Hello everyone, I'm Siyi Zhou from Stockholm University. Today I'm going to talk about classical string solutions on de Sitter space. This is based on our archive paper last year and several ongoing ones with these collaborators. The outline of my talk is as follows. First, I will talk the motivation of our work. Then I will proceed to talk about rigid trajectory in de Sitter space. Afterwards, I will talk about high-energy scattering. I will also talk about different classes of string solutions. There are strings with internal dimensions and also spiky strings. I will give a summary in the end. It is notoriously difficult to construct de Sitter vacua in string theory. The reason is the Marcina-Nunes no-go theorem. KKLT evades the no-go theorem by breaking some of its assumptions. However, it contains non-perturbative effects and it is not fully understood yet. So the question we want to ask ourselves is can we have a consistent worldsheet theory on de Sitter space? We try to tackle this question from the following two perspectives. The first one is the Higuchi bound in de Sitter space, and the second one is the modification of the rigid trajectories. So now I'm going to review the Higuchi bound. The Higuchi bound is a unitarity bound on the mass of the higher spin particle in the de Sitter space. It's m squared larger than s times s minus 1 h squared for bosons, and m squared larger than s squared h squared for fermions. Here, m is the mass of the particle and s is the spin of the particle. Particles with masses violating the Higuchi bound contain holistic modes with a negative norm and thus is prohibited by unitarity. The Higuchi bound can be shown on this m squared versus s plot here. As you can see, the blue region is the region that is prohibited by the Higuchi bound. From this plot, you can also see a purple straight line. This purple line is a naive extrapolation of the familiar flat space rigid trajectory to the de Sitter space. If we do so, then you can see that at some point, this linear rigid trajectory violates the Higuchi bound. As we can easily calculate, this is just the red dot shown here on the plot. As you can easily calculate, the point will have a critical mass of m squared over h and a critical spin of ms squared over h squared. A typical length of the string at the critical value is near the Hubble horizon scale. One may use this to show that de Sitter space and string theory are incompatible with each other. But is this really so? We want to consider this question in more details, especially we want to consider how the rigid trajectory is modified in de Sitter space. First, we review the rotating folded string in flat space. A rotating folded string in flat space will be influenced by the centrifugal force and the string tension. The balance of these two forces requires the boundary have the speed of light. Now we talk about how we obtain the solution of the semiclassical string in de Sitter space. This is fairly easy. First, we consider the static coordinate of desired space. Then, we make a change of the variable r equals to sine rho. Then, we obtain a metric of the form shown on the second formula. Afterwards, we can do a weak rotation. Rho goes to minus I rho, t goes to it, r squared goes to minus r squared. In this way, we obtain the global coordinate on de Sitter space. So the take-home message of this slide is that the static coordinate of de Sitter space is related to global coordinate on the de Sitter space by a simple weak rotation. Now we consider the rotating folded string in de Sitter space. Apart from the centrifugal force and the string tension that rotating folded string in the flat space also has, the rotating folded string in de Sitter space is also influenced by the Hubble expansion. In the case of rotating folded string in de Sitter space, the boundaries also have the speed of light. Since we consider the semi-classical string, it is enough to consider the simplest Nambu-Goto action shown here. Taking a variation of the Nambu-Goto action gives the following string equation motion. The first line in the equation motion is the same as the flat space equation motion, and the second line of the equation motion is unique to curved space. As you can see here, it involves a derivative on the spacetime metric. Now we consider a specific spacetime metric, the de Sitter 3 cross S1 metric shown on the first formula here. We can choose t equals to tau gauge for simplicity. The rigid string ansatz we take are rho equals to rho sigma, phi equals to omega t plus n sigma, curly phi equals to nu t. The folded string corresponds to n equals to 0 and nu equals to 0. Folded string with internal charge corresponds to n equals to 0 and nu unequals to 0. The spiky string corresponds to n equals to 1 and nu equals to 0. The energy, spin, and the internal U1 charge J can be derived in a straightforward manner, and the result is shown here. In the following, we first discuss folded strings with n equals to 0 and nu equals to 0. Now we can plot the leading rigid trajectory on the same plot with the Higuchi bound. We can find that the curved space effects will modify the rigid trajectory to make it consistent with the Higuchi bound. You can also see a sharp turning point here. This means that there exists a maximum spin on the trajectory. You can also see after the trajectory turns left, it ends on the point of vanishing spin and finite energy. This is because the longest string touching the horizon must have a speed of light, which in turn forces it not to rotate. The conclusion we got from this plot is that the spectrum of long strings on de Sitter space is qualitatively different from the flat space and ADS. The longest string has a vanishing spin and a finite mass due to the accelerated expansion. One might feel puzzled by the sharp turn of the trajectory. but we can plot here individually how the spin and energy square changes when we vary the length of the string. Here, rho 0 equals to 0 means very small string, and rho 0 equals to pi over 2 means a large string with boundary touching the horizon. As we can see from the plot, the spin first increases when we increase the radius of the string, but then it starts to decrease when we further increase the radius of the string. At the horizon, the spin of the string vanishes. As the length of the string increases, the energy squared also first increases and then decreases, but it decreases to a finite value. Here we consider the short string limit of the folded string. When we take the short string limit, it means essentially that harbor horizon is very large compared with the size of the string, so the string effectively lives in a flat space. As expected, when we take the short string limit, we recover the linear rigid trajectory. We proceed to consider the long string limit. When the string touches the horizon, rho 0 goes to pi over 2. This means that the angular velocity of the string will approach to 0. In this situation, space-time curvature is not negligible. We can see here the energy goes to a finite value, but the spin approaches to 0. Now we consider the high energy scattering. In string theory, existence of an infinite higher spin tower is crucial to make mild the high energy behavior of the scattering amplitudes and to UV complete gravity in a weakly coupled regime. The existence of a maximum spin in the de Sitter rigid trajectory makes it non-trivial to maintain the mildness of high energy scattering. So we consider two possibilities. The first is that the UV completion is achieved by considering only the leading rigid trajectory. The second possibility is that the UV completion is achieved by multiple rigid trajectories. We first look at the possibility that the UV completion is achieved by only the leading rigid trajectory. In this case, in order to UV complete gravity in a weakly coupled regime, we would need sufficiently many higher spin states from the string scale up to near the Planck scale. The mass of the maximum spin state in the leading rigid trajectory has to be bigger than the Planck scale. This condition implies an upper bound on the vacuum energy of inflation. We have derived that the vacuum energy must be smaller than ms to the fourth power. This then implies an upper bound on the tensor-to-scalar ratio. R must be smaller than 0.01 if the string scale appears at 10 to the 16 GeV. Note here that the M Planck can be the Planck scale in higher dimension, which makes the bound weaker. Now we consider UV completion of multiple rigid trajectories. The higher trajectories correspond to unfolded strings. The shapes of the unfolded string is shown on the right-hand side of the figure. From bottom to top, you can see one-folded string, two-folded string, three-folded string, and four-folded string. For the unfolded string, the energy is n times the energy of the one-folded string, and the spin is n times the one-folded string as expected. As we can see from the plot, the turning points are nicely aligned on a parabola, and no matter how many times we fold the string, they will never violate the Higuchi bound. Now we start to consider strings with internal dimension. I remind you again that we consider the de-Sitter-3 equals S1 metric, which means n equals to 1 and nu does not equal to 0. The strings are rotating around the S1 cycle of the internal space, and the motion along the cycle is stable. This means that the cycle S1, is its big circle. Here, the curly phi stands for the angle of the internal cycle S1. Here, I remind you about the non-Bour action of the string with internal dimension, its equation motion, and the condition that the end point of the string must satisfy. Again, I remind you here about the energy spin and the internal U1 charge of the string with internal dimension. In this plot, we show the leading rigid trajectory of the string with internal dimension. This is an E square versus S plot with different values of nu chosen. As we can see from the plot, when we increase nu, the trajectory actually goes higher and higher. Then there's no worry for this case that the string with internal dimension will violate the Higuchi bound. In this plot, we still show the leading rigid trajectory of strings with internal dimension. The different thing in this plot as compared with the last one is here, instead of plotting the rigid trajectory fixing different values of nu, we fix different values of j. The different feature we discover here is that, first of all, the turning point becomes sharp. In addition, the starting point is no longer the origin. Now we consider the spiky strings living in the de-Sitter-3 subspace of de-Sitter-3 equals S1. In this case, we have n equals to 1 and nu equals to 0. The plot on the left-hand side is what you might be very familiar with. It is the shape of the spiky string in anti-de-Sitter space. On the right-hand side, it is the shape of the spiky string in de-Sitter space. As you can see from the plot, the shape of the spiky string in de-Sitter space is slightly fatter than the shape of the spiky string in anti-de-Sitter space. Now we come to the rigid trajectory of the spiky string in de-Sitter space. Here we plot the rigid trajectory corresponding to different spikes. As usual, On the down left corner of the plot, you will discover that the short strings behave like the usual flat space rigid trajectory. On the upper left corner, all the long strings actually end at the same point with vanishing spin but finite energy. No matter how many spikes they have, they end on the same plot. This is confirmed by our analytical computation. So how to understand the spiky strings with different spikes actually end on the same plot on the E square versus S plot? To help you understand this, we show you an example of the spiky string with 8 spikes. On the left-hand side, you see short spiky strings, and on the right-hand side, you see long spiky strings. The short spiky strings really have the spiky shape. However, the long spiky string does not have spiky shape anymore. Instead, they really look like circular strings. No matter how many spikes they have, they all go to the same circular string limit. A calculation shows that in this case, the size of the long spiky string is half of the horizon size. This is the longest spiky string we can have when we have many spikes. They are still rotating, but they still have non-vanishing angular velocity. However, due to the circular-like shape they have, they do not have spin. Now it is time to give a summary of my talk. First, I talk about how string rigid trajectory is modified in de Sitter space. Next, I talk about the fact that there exists a maximum spin for each trajectory. Then I talk about the fact that semi-classical string spectrum on de Sitter space is consistent with the Higuchi bound. Then I pointed out that if the UV completion is achieved at the leading rigid trajectory, then there exists an upper bound on tensor-to-scalar ratio under some assumptions. We talk about other types of semi-classical string solutions, especially the strings with internal dimension and spiky strings, and their interesting properties. That is all of my talk today. Thank you very much for your interest.